Hello everyone, it's Dr. C. Happy Friday. I'm sitting at home looking out my back window recording a pre-lecture for you guys, so this is kind of fun. So just to remind you, where we are in the course, we finished the thermo part. Is a reaction spontaneous? Is it going to happen? And now we're looking at reaction rate. How fast or slow is a reaction? And one of the big focuses is what are the different factors that affect rate? Concentration, temperature, activation energy, okay, things like that. So we started touching a little bit on collision theory, and this is really the concentration piece. Molecules must collide to react. That's what collision theory says. So the more collisions we have per second, the faster the rate. And so that's what I have circled on the screen here, okay? And that should make sense. Reactants have to come together to react. The higher the concentration, the more chance the reactants are going to come together. All right, so that's kind of the start where kind of rate, where rate is tied to concentration, and we focus more on molecules must collide to react. We looked at that slide. Let's skip that. We also talked about, well, they not only have to collide, they have to collide with enough energy. And that minimum energy to initiate a reaction is called the activation energy. I apologize. I forgot. Sometimes I need to mute my other mic on my computer. So I'm using a lapel mic, and then there is a mic on the computer. So hopefully that wasn't too bad. If not, I'll go back and record. So they have to collide with enough energy. If they don't have enough energy, no reaction takes place. Okay, and that minimum energy is called the activation energy. So we've talked about that. And the activation energy is shown here. There's that energy barrier, that energy we have to put in, even for a spontaneous reaction, to make that reaction happen. But once it starts, it's going to continue on its own without outside intervention. Okay, and that's what we mean by spontaneous. Temperature definitely will affect rate. And you can see that, and I need to scroll up just a little bit more, as we increase the temperature, the rate constant, and hence the rate increases, because rate is proportional to the rate constant. Rate constant goes up, rate goes up. All right, and this makes sense. If we put in more kinetic energy, the molecules are going to collide with more energy. And so more collisions will exceed that energy barrier, that activation energy. All right, having trouble scrolling today for some reason. All right, so here's a little more detail on why the rate increases with temperature. All right. Normally, because there's going to be, potentially billions and trillions of collisions per second, but only the fastest moving ones are going to have enough energy in that collision to exceed the activation energy. Okay. Now, at higher temperature, as we've already kind of hinted at, there are more high energy molecules. Okay. We put more kinetic energy in, they're going to collide with more energy. And so let's look at a couple of graphs here. One just showing you this is nitrogen gas, so N2 gas. And just to show you as we raise the temperature. Now, you see a distribution here. There's always a distribution of speeds for particles of a substance, right? They're not all moving the same speed. But if we look at the average for all of these, clearly as we raise the temperature, the molecules are moving faster, they're going to collide with more energy, and hence more of those collisions will exceed the activation energy. All right. And another way to look at it, this is from an different book, but here's a slide from the current book, and now it's showing this is the higher temperature, T2. All right. These are all the molecules that have enough energy to exceed the activation energy, all the collisions, not the molecules, but they're going to collide with enough energy. And you can see at the lower temperature, that's kind of shown in more purple color here, T1, the fraction of molecules that exceed the activation energy is smaller. And at the higher temperature, which is kind of shown in orange here, there's many, many more molecules that when they collide, you'll exceed the activation energy. Okay, I think this is pretty intuitive, but things to consider in terms of what's going to affect rate. We did talk a little bit about potential energy profiles in 151. We've shown some of these. I think I even showed some of these back in the thermo chapter. Make sure you know when you look at a potential energy profile whether it's exothermic or endothermic, just by the shape of that potential energy profile. And I think I have a couple that follow here. Again, these notes are posted in Blackboard, so you don't have to write all this stuff down. You might want to print them out and take some notes on those slides. So here are two potential energy profiles. Again, reactants on the left, products on the right. We're looking at reaction progress going this way. Here is our energy barrier. Okay, we're going to talk about the activated complex in just a minute. And then this distance between reactants and products, that is our delta H, if that reaction is run at constant pressure, which we will do quite often. All right. It's actually the internal energy change if it's not, and we're not going to really go into that. Okay. Now, the products are more stable. They're at a lower energy than the reactants. This energy will be released as heat. This is exothermic. Okay. Products are more stable, lower energy. That energy is going to be released. That energy difference is going to be released. This one, on the other hand, is endothermic because we have to add energy to get from reactants to products. This is our delta H, our heat flow at constant pressure. Okay, so make sure you can look at these profiles. And what you'll notice, in general, the activation energy is going to be larger for endothermic reactions, just based on the shape of this profile, with products being at a higher potential energy, less stable. It's almost always going to make that activation energy larger than your typical exothermic reaction. And we can obviously relate that to reaction rate. All right, let's look at one example where we talk about what an activated complex is. That's right at the top of the curve. And I don't know how I jumped all the way to the end of my slides. Recording live is so much fun. I just completely... Okay, you guys got all this. We're done with the chapter. It's all good. There's catalysts. There's all this other stuff. We don't need to do chapter 14 anymore. Let me see if I can find where I was. I was here somewhere. Oh, I'm getting close. Okay. So here's a very simple reaction. This is called isomerization because we're forming what's called an isomer. It has the same formula, but the atoms are arranged in a different way. So all that's happening in this reaction, well, let's go to green for a while, is that CN triple bond, it's actually bonded through the nitrogen here, is going to flip, and now we're going to have a bond to this. This is called a methyl group through the carbon rather than nitrogen. Okay, so same formula, but different structure. So that's an isomer. All right, so essentially this bond has to break here, and then that molecule, that group, that CN has to rotate, and we have to form a new bond, in this case to the carbon. Okay, so we're going to have to put in some energy to initiate that bond breaking, and that's going to be our activation energy. All right, so here we are. There's there might be collisions with molecules, or maybe there's enough energy to start this wagging process. Okay, so bonds are constantly moving. They're stretching, they're bending. Okay, so this bond starts to bend. Not enough energy yet, not enough energy yet. But eventually there's going to be enough energy to flip to a particular structure at the top, okay, at the very top of this activation energy. And that complex is called the activated complex. And it's going to be a structure that's in between the reactants and the products. In this case, it's going to be partially broken bonds of the reactants and partially formed bonds of the products. Okay, partially broken and partially formed. Okay, so this is kind of, along the way from reactants to products, what does the structure look like? And that is our activated complex right at the top of that energy barrier. So let's see what that would look like for this reaction. And there you go. So maybe it's better to look at a diagram here where this bond has wagged enough and moved up so that we kind of have a little bit of a bond to the nitrogen and half, maybe you can consider it half a bond to nitrogen, half a bond to the carbon. And I got it backwards. Nitrogen's blue. So half a bond to nitrogen, half a bond to carbon. Okay? And we could also just show it with this structure with dotted, that there's a kind of a partial bond across like that. And then, once we reach that barrier, once there's enough energy to start breaking that bond, we can then rotate and form this new bond to carbon. Okay, so another name that you will hear used for that activated complex is the transition state. We are transitioning from reactant to product. Okay, so activated complex, transition state. I'll try to use activated complex because I think that kind of leads you to think about a molecule that's at a higher energy, okay, activated, it's up higher, and it's a complex that's, kind of in between reactant and product. All right, last thing we did in class. I kind of jumped ahead, so I skipped a lot of the stuff with the potential energy profiles that we just went through because I wanted to get to this Arrhenius equation because it is in ALEX this week. And the Arrhenius equation is actually really cool. You're not going to think it's as cool as I think it is, potentially. But it puts all this stuff together in one equation. It has the rate constant, and we know rate is proportional rate constant. So it has rate in it. It has temperature. It has the activation energy. It has something called the frequency factor, which deals with collisions and how the molecules are oriented. So it's putting together in one relatively simple equation pretty much all the factors that are going to affect our reaction rate. Concentration, because if we have higher concentration, we have more collisions. The temperature, the energy barrier, all of this goes into one equation. Now, we won't use this form of the equation very often because we can get more useful forms of the equation. And this particular form of the Arrhenius equation, okay, where we take the natural log of both sides, and don't worry about the math, I will give you this modified form. Natural log of K is equal to minus EA over R times 1 over the temperature plus natural log of A, the frequency factor. That is a straight line equation. It is linear. Okay, so our y value is natural log of K. Our x value is 1 over the temperature. All right, so if we plot, so what you do experimentally is you would run a reaction at many different temperatures, say 5 different temperatures. You'd measure the rate and determine the rate constant. And then you would make a plot of those 5 points. Okay, did everybody hear that? So run the reaction at, say, 5 different temperatures and determine the rate constant at those 5 different temperatures. Because remember, the rate constant changes with temperature. Okay, it's a constant at a given temperature for that reaction. And then the next slide here, once we collect our data in the lab, and hopefully we've collected good data, we plot our data. Here is our y value, natural log of K. Here is our x value, 1 over the temperature. And we plot our data. Okay. Now, what the data we're going to collect is we're going to have the temperature and we're going to determine the rate constant. We're going to have to take the natural log of the rate constant to plot, and we're going to have to go 1 over the temperature to plot. But the cool thing about that plot, and this could be an experiment you do in lab, you actually do not do this in the 152 lab, but it's a pretty cool experiment. If we go back to our line, the slope of that line is equal to minus EA over R. So we can determine the activation energy from the slope of that line. So we get the slope. R is a constant. It is the gas constant, but with units of energy. And all we have to do is take the slope times R, change the sign, and we get the activation energy. So let me show you an example of that. I'm about out of time here. Here's a plot I made it easy for you. This is the handout from class. If you don't have this, check the handout folder in Blackboard and print one of these out. This one I just told you what this, I just give the slope. So you have to then realize that because we're plotting natural log of k versus 1 over temperature, that slope is equal to minus EA over R, or EA, and I'm going to rearrange, slope times R, and that will be negative. Okay? So this has a negative slope. Activation energies, always positive, always. That's energy we have to put in to initiate that reaction. Okay? So let's see if you can get this right on the pre-lecture quiz. I'm just going to put this in the pre-lecture quiz. I've set it up for you. Slope is right here. Plug that in. Plug in R, 8.314 joules per mole Kelvin. Be careful, so you just multiply those two things. Make sure you end up with a positive activation energy. Okay? They're all positive here listed. And I'll just put this one right on the pre-lecture quiz. I might not be able to put the graph on there, so if I put a problem on the pre-lecture quiz that says refer to the graph in the handout in problem 3, that's what I'm talking about. Okay? Now watch your units. You're going to end up with joules because R is in joules. Activation energy is almost always expressed in kilojoules, so you're going to have to convert from joules to kilojoules. Okay, that's where I want to leave off here. I just do want to show you one equation. If you're working ahead in ALEX and you see, let me switch back to my notes, a problem that gives you a couple of rate constants and a couple of temperatures, we can come up with another form of the Arrhenius equation that's a little simpler than the one we just looked at, because the other one we're going to have to collect data, probably at least 4 or 5 points, and then measure the slope, determine the slope, and then calculate activation energy. There's an easier way to do that by just taking 2 points, 2 rate constants, 2 temperatures, and coming up with this equation. Okay? So essentially we're taking the equation on the previous slide, and we're taking that equation at one temperature divided by that equation at the other temperature, and it then modifies into this form. So if you know only 2 temperatures and 2 rate constants, same R, we can solve for activation energy. Okay? So I'm not going to give you this calculation on the pre-lecture quiz, but I wanted you to see this in case you do this in ALEX. We will do a couple of these in class with this equation, just to make sure you're able to manipulate. This equation can be a little tricky to manipulate with the natural log of the rate constants, and the 1 over t algebraically manipulating can get a little tricky sometimes. All right. I think that's it for a Friday. I went a couple minutes longer than I wanted to. I apologize. I get talking, and I could go on for days. Well, maybe not days. I might have to sleep sometime. I hope you're doing well. I hope you have a great weekend. If you have any questions, send me an email. I will be checking my email periodically this weekend. And, try to get a good start on ALEX. Do the knowledge check. And if you're open pie, go back and work any problems that ALEX decides to take away from you. Okay? All right. See you on Tuesday. Don't forget I have office hours Monday, Tuesday, Wednesday, so maybe I'll see some of you on Monday. All right. Have a great weekend. Take care.